The main point of the lesson is to practice past papers, but I obviously do need to remind you about some theory, especially some theory that people struggle with. So starting off on the screen, we have a summary of all the quantities that you need to know, the symbol that represents those quantities, and the unit for those quantities. So you can see, for example, current. The symbol for current is I, but the unit is amperes, A. So there's a difference between symbol and unit. And the reason I'm putting this on the screen is because some grade 10s, even some grade 11s, and even some matrics get confused between symbol and unit. So that's why I put an example there for each of them. So if I say the voltage is 3 volts, then it's V equals 3V. Or if I want to say the current is 3 amperes, another way to write that is the current is equal to 3 amperes. You need to understand the difference between I being the symbol and A being the unit. It's like me saying that my height is 100 and, I don't actually know, 55, 52, I don't know, whatever, centimeters. Do you see the difference? H is a symbol for height. Centimeters is a unit for height. They're very different things. Okay, so that's that. Then just looking at the formulae quickly. Okay, so the formulae on the screen, let's go through them quickly. Both of these are measure of resistance. Oops. That's to measure resistance. And we know the top one is if our resistors are in series. So for resistors connected in series, we just add the resistance, R1 plus R2. And this is for parallel resistance. I'm going to go over those two differences now. And resistance is measured in ohms. So the symbol is R, but it's measured in ohms. Q, we did a whole lesson yesterday on Q being the measurement of charge. So Q stands for charge, and the unit for charge is coulombs. So for example, if you want to say 3 coulombs, you say 3C. So the charge is equal to 3 coulombs. I is current, measured in ampere, and delta T is change in time. And please, guys, for this formula, time is measured in seconds. You have to convert if it's not given to you in seconds. Okay, R is resistance. We said V in both of these formulae are voltage or potential difference. They often call it potential difference, not voltage. Potential difference. Potential difference is voltage, so don't get confused. When they say the potential difference across a resistor is 3, then it's 3 volts. The potential difference is 3 volts. I is current. W, this is very important, and people often forget about this. W is work done or energy transferred. Energy transferred. It means the same thing. And you might be confused. You might think, but W stands for work. Why are you saying energy? Work and energy are the same thing, basically. So if you see W, it can mean work or it can mean energy. And the unit for both of those is joules, J. This is an example of resistors connected in parallel. This over here is the same circuit. It's just drawn differently. We can see that there's a split in the branch over here. So the total current is represented in yellow, and it splits. Some of the current goes through R1, the rest goes through R2. This over here is exactly the same, the circuit on the right. These ones over here also representing resistors in parallel. The current splits here. So everywhere over here that I'm highlighting in blue, that's total current. Total current of the circuit. Then it splits. Then some goes to the 7, some goes to the 15, and then it joins again over here. Same thing here. This would be total current, and then it splits. And same thing at the bottom. You need to be able to identify circuits, resistors in parallel versus resistors in series. I hope that you can see. Imagine this is the battery over here. I know this is not how we draw our circuits, but anyway. This is the total current. Again, down there, total current. And then the current splits. So some of the current goes that way, some of the current goes that way. For the circuit over here, if I tell you this is the battery, then which resistor is in series at the moment with the battery? So this is the main line of the circuit. If we take our finger and put it on the current, we go down. This is the total current. So the total current flows through R1. And the total current flows down here. Then what happens is, I hope you guys can see that there's a break. There's a split over here in the circuit. Some of the current will go through R4, and the other bit of the current will go through R2 and R3. So the total current will flow through R1, and then R2 and R3 are in series with each other, but they're in parallel with R4. If I have to work out the resistance of this circuit, I don't know if you guys can tell, but this is the parallel resistors. So to work out the resistance in parallel, you go 1 over RP equals 1 over R1 plus 1 over R2. Now, what people don't understand is that this 1 over R1, what people forget, 1 over R1, so R1 would refer to this branch. R1 refers to a branch. R2 refers to this branch. So when you work it out, it's 1 over R1, but R1 is 8 plus 4. So it's 8 plus 4, or 12, but you can write 8 plus 4 there, plus 1 over R2, and R2 is 12. I don't know if that makes sense. Therefore, 1 over 12 plus 1 over 12 is 2 over 12. That's 1 over RP. Inverted, so RP is equal to 12 over 2. You flip the fraction. You invert this one. You invert this one. Reciprocals. 12 over 2 is 6 ohms. But that's not the total resistance. So basically, guys, you need to understand what this means. That means that overall, for this part of the circuit, this part as in that part, overall that part of the circuit has a resistance of 6 ohms. That's what that means. Therefore, the total resistance, R total, is that 6 ohms, which I just calculated, which is the parallel stuff, plus this one. So 6 plus 6. It's a lot of 12s, but it ends up being 12 ohms. Okay. Series versus parallel. This is just some theory that you need to know. In series circuits, the current is the same everywhere. In parallel, the current splits. That's what we were speaking about. In series, the voltage splits. In parallel, the voltage is the same. And there's your formulas for calculating resistance. So I wanted to show you this with an example. So over here, in this parallel circuit, here, if I look at this, I've highlighted in green the total current. So if you look at the parallel circuit, you see the total current is in green, and then it splits. Some of it goes through the top one, and the rest goes through the bottom. Now, I don't have the value for the total current over here. I could work it out, but let's just pretend the total current is 6 ampere. How much will go in the yellow branch and how much will go in the blue branch? Same resistance, 1.5, 1.5, which means that 6 amperes would split evenly. It would be 3 amperes here and 3 amperes here. And then when it joins back again, it's total current again. Over here, the series circuit, do you see here, they give you total currents. The ammeters always reads current. That's very important. Voltmeters reads potential difference. So here they give you the total current 1.5 amperes. So the one question asks, what does ammeter A2 read? This is A2. So if A1 reads 1.5, this is a series circuit. So A2 will also read 1.5. So everywhere the current is the same. So through the battery, through the 2 ohms, through the 4 ohms, wherever you are on the circuit, the current is the same. Voltage or potential difference for resistors connected in parallel is the same. So if you look here, they give you the voltage for this circuit across the battery. It's 9 volts. If you can look carefully, you'll see that for circuit A, there's no resistors connected in series. What that means is all of the 9 volts goes to the resistors in parallel. So this thing will read 9 volts, V2 will read 9 volts, and V1 will read 9 volts. So for resistors connected in parallel, the voltage is the same. Even if I had to connect one massive voltmeter over here that reads the voltage across both of them in parallel, it will also read 9 volts. Okay, so if I had to add another resistor next to it, let's say that it was also 1.5 ohms, then what will happen is, again, you look at it in terms of branches. So the top branch will get 9 volts, okay? because the battery's 9 volts, the top branch will get 9 volts, and both of these together will get 9 volts. The branch as a whole will get 9 volts. And because they're equal in resistance, they'll each get half of 9. So 4.5 and 4.5. Let's say the voltage across the battery is 10 volts. Then we know that the voltage across this whole parallel thing is 10 volts. What that means is the voltage across the top branch, if I have to connect a little voltmeter here, that would be 10 volts. And if I have to connect a voltmeter across the bottom branch, it will also be 10 volts. So it's about the branches. But because there's two resistors, and let's pretend they have exactly the same resistance, let's say 2 ohms here and 2 ohms here. If the branch gets 10 volts, then this resistor, if I have to connect another voltmeter over there, this resistor will get 5 volts and this resistor will get 5 volts. Because remember, voltage splits in series, and technically these resistors are in series. So for the branches, the parallel branches, voltage is the same. Over here, just try and focus and see if this makes sense. Some of that voltage will go to this resistor, and the leftover voltage will go to the parallel resistors. So let's pretend that this voltage over here is 10 volts, and then let's say 2 volts of that goes to this light bulb over here. Then 8 volts will go to the resistors in parallel. That means that this one over here will get 8 volts, and this one over here will get 8 volts. Okay, so basically the total voltage splits between this piece of the circuit and this piece of the circuit. The parallel stuff functions as one like piece of the circuit basically. So V2 plus V3 will give me V1. And then the current, the total current flows through the main line of the circuit, which is here, total current, and then it splits. Half of the current will go that way and half of the current will go that way. And why am I saying half? How do I know that it's going to be a 50-50 split? Both resistors are the same. If the resistors aren't the same, then you can't assume it's going to be 50-50 splits. Okay, let's do a question. Okay, so it says, is the voltmeter reading of 6 volts the EMF or the potential difference? You just need to know EMF briefly. If the switch is open, it's going to read the EMF. So I'm just going to write a note for you here. If the switch is open, so open switch, then the voltmeter across the battery will read the EMF. If the switch is closed, so closed switch, then it'll read the potential difference of the circuit. So the answer here is the 6 volts, the reading the EMF or the potential difference. It is the potential difference because the switch is closed. That's it. Okay. Then calculate the total resistance of the external circuit. So if they say calculate the total resistance or calculate the effective resistance, it just basically means the total resistance. So over here we can see we have a parallel part of the circuit. So we have to go 1 over RP equals 1 over R1 plus 1 over R2. So you always do the parallel part of the circuit first. Never ever combine your parallel combination with your resistor in series combination. So absolutely do not say plus 2 in the same question. No, that has to be done separately. Okay, so we're going to go 1 over, remember R1 is going to be your top branch. So 1 over 2 plus 1 over R2. So this is your other branch, 1 over 2. So it's 1 over 2 plus 1 over 2. The resistors are exactly the same, which is 2 over 2. This is kind of a boring one, because when I flip it, it's exactly the same. So 1 over RP is 2 over 2. So RP is also 2 over 2, which is 1 ohm. But that's not your answer. That's your parallel resistance. So therefore, you guys know I do therefore like that. Your total resistance is your parallel resistance, which is 1 ohm, plus your resistance in series, which is 2 ohms. So this has a resistance of 1 ohm plus that 2 ohm over there. So my total resistance is 3 ohms. You need to put your unit or I'm not going to give you your mark. Calculate the reading on A1. Okay, now when they ask for a reading on A1, that's an ammeter. Ammeters measure current. So you need to look where A1 is. Just be careful that it's not in a branch. But A1 is over here. So A1 is going to measure total currents. And it's very important to remember that when I want to determine total current, I need total voltage. Total voltage and total resistance. That makes sense. If you're trying to work out total current, you need to use total V and total R. So current is equal to V divided by R. That formula is given to you. Please, if you're going to rearrange formulas, please make sure you know how to do it properly. So total voltage is 6. Total voltage is the voltage across the battery. And total resistance we just worked out. It's 3. So my total current is 2 ampere. Remember your units. You can do the most beautiful calculations for me, formula, substitution, but if you don't put the A there, you're going to get 2 out of 3, which is, I mean, why get 66.666% when you can get 100%? You know what I mean? Now, calculating the reading on V1. Look where V1 is. Please always, when they ask you something, always make sure you look where it is. V1 is over here. It's connected across the 2 ohm resistor. So V, calculate the reading on V1, we want voltage. We know V is equal to I times R. So the current that I use, now you guys tell me, is it going to be total current that flows through here, or is it going to be a split current? Total current. Yes. So I is total current, and R, now it should make sense that if I'm trying to find the reading on V1, V1 is connected across the 2 ohm resistor. So the R that I use is 2. So 2 times 2 is 4 volts. That's it. Now they want the reading on A3. I think this is a very easy electricity question. Remember we calculated total current was 2 amperes, and they want to know the reading on A3. So A3 is inside a branch. So that means that the current, the total current, which is 2 amperes, is going to split. But because the resistors are the same size, resistor, it's 2 ohms to 2 ohms. It's going to be a 1-to-1 split. So it's literally going to split evenly. So therefore, the reading on A3 is going to be 1 ampere. That's very easy. This question I think was a little bit more difficult. This whole story, always read the stories before your questions. They got V1 is connected across the battery. So V1 will measure total voltage, total V. The switch is initially open. So when the switch is open, this thing will initially read the EMF. When it closes, it's going to read total potential difference. V2 is connected across the 35 and resistor R. Do you see that? So this voltmeter will read the voltage across both of these resistances. Okay, but we don't know what resistor R is. And my question was, which ones are in parallel? So you can see that 35 and R are in series, and over here is where the split happens. So that means the 22,5 and the 18 ohms are in parallel. V3 measures the voltage across the parallel resistors. So that measures voltage in parallel. So basically, if I take V2 and I plus the voltage in parallel, which is V3, I'm going to get V1. So those sorts of things need to make sense to you. That's, if you know that, then you know you understand the principles of electricity. Then it's just knowing which formula to use and when, and practicing it. So if I add this voltage, V2, and I add the voltage across the parallel stuff, I'm going to get the total voltage. Okay, cool. And then A1 is total current, and then A2 measures a split current. So let's actually see what questions they have for us today. First question, determine the effective resistance of the resistors in parallel. And then they say they close the switch and they give us a bunch of readings. So let's first do the effective resistance in parallel. So we go 1 over RP equals 1 over R1 plus 1 over R2. R1 is 22,5. It's this branch. Okay? Plus R2 is 18. It's this branch. If there were 2 resistors in the branch, we would add them first and then put that number there. But luckily, we only have 1 in each branch. 10, that's 1 over RP. So therefore, RP is 10 ohms. Okay, that's it. That's it to work out effective resistance in parallel. The switch is now closed. Okay, so they're closing that switch over there. Then V1 is going to read total potential difference or total voltage. And they tell me that that is 120 volts. And A1 is measuring 1,5 amperes. So that's measuring 1,5 amperes. And look where A1 is. It's connected in series. It's not in a branch. So this is actually the total current. Then they want to know the reading on voltmeter V3. Now remember we discussed that V3 is connected across the voltmeters in parallel. Sorry, the resistors in parallel. So basically they want voltage in parallel. We know V is equal to I times R. So V is equal to I times R. The resistance that I'm using is going to be 10. We just calculated that in the previous question. It's this. It's the effective resistance or the total resistance in parallel. It's the overall resistance in parallel, which is 10. We just calculated it. You can't use 18. You can't use 22,5 because we're looking at the overall or the effective resistance in parallel, which is 10. And then the current that we use, I know current splits. So some of it's going to go through the 22,5, some of it's going to go through the 18, but overall, for this piece of the circuit, for the parallel combination, the total current will flow through there. So 1,5. That is 15 volts. It'll be formula, substitute, answer with unit. Then the next question is supposed to be a more difficult question. Calculate the value of resistor X. It should be resistor R. Sorry, I think there was a typo in this paper. This should say resistor R. We want to find resistance of resistor R. We know that the total current will flow through resistor R. But we don't know the voltage across resistor R. Remember, if you're looking for resistance, if you know current and if you know voltage, you can find resistance because we can do R is equal to V over I. But in this case, we have a little bit of a problem because we know the total current will flow through resistor R, but we don't know the voltage over R. But what I can calculate is the voltage over both of these. And we can work backwards like that. So what I'm going to do, calculate basically what the resistance is over here for both of these together. I'm basically looking for this total resistance for this piece here that I keep highlighting. So if I want to look for the total resistance of that piece, the 35 ohm and resistor R, I'm going to use the voltage across them, which is V2, divided by the current that flows through them, which is 1.5. But another problem, how am I going to find V2? How do I find V2? Well, remember, we discussed earlier that the total voltage, which is 120, which is over V1, some of it is going to go to the V voltage in parallel, and the rest is going to go to V2. The total is 120, V1, and 15 goes to V3. How much is left over for V2? V2 is basically 120, the total across the battery, minus 15, which is 105. Now that I have the total voltage across both of these, so basically V2, I can take that, 105, and I divide it by the current that flows through those two, which is 1,5, 70 ohms. You need to understand what that represents. Because I used V2, I used the voltage across both of them. That 70 ohms is for 35 plus R. It's for both of those resistors. So 35 plus R gives you 70. Then R has to be 35. These questions they always ask, so you need to know how to do them. If I add another resistor in parallel with the 18 and the 25.5 resistors, what happens to the total current? Now, people always get this wrong. So if I add another resistor, first tell me what happens to total resistance. Does decrease. So therefore, what happens to total current? Increases. Good. Remember the relationship between resistance and current, hey? So it's inversely proportional. So let me explain first of all why total resistance decreases. Remember, if we add another resistor in parallel, we're basically giving the current more options. So I taught this, I used the analogy of like, if I have one passage that goes from one side of the school to the other side of the school, there's going to be a lot of traffic. It's going to be a very high resistance. But if they open more passages that go from the one side of the school to the next side of the school, there's more pathways for the current to flow through. So there's not going to be a lot of traffic. There's not going to be a lot of resistance. So if I add another resistor, I'm adding another pathway. So resistance decreases. Total resistance decreases. And whatever resistance does, current does the opposite. So total current will increase. And your reason for this is if I add a resistor in parallel, total resistance of the circuit decreases. And the reason why is because current is inversely proportional to resistance. Or you can write it in words. Inversely proportional, which means when the one goes up, the other goes down. Or when the one goes down, the other goes up. And what must stay constant? So there's three variables technically. There's R, there's I. If we're saying these two are inversely proportional, then voltage has to be constant.